Hi, welcome to cost function session. Here the least square error can be represented in the plot for the given four data points as shown here. This is the data point 1. For the data point 1, this is actual value, this is the predicted value. So the difference between the predicted value and actual value is represented as a error 1. So it will be squared up by using the least square error method. And the data point 2, this is the data point 3 and the data point 4. So the data points on the decision boundary is predicted value, and the violet color is represented in the form of actual data point. Now how to minimize this error? The minimizing the error in the sense, here we want to reduce this error between all the data points. So we can do that by updating the parameter theta. Here the x is already fixed one, so x is the data set which is given already in the problem statement. So this x value, for example 1.2, 2.3, here 1.0, 2.0. So this data set cannot be changed, but we can update the parameter value for each and every iteration. So by updating the parameter, we can reduce the error close to the 0. So if you are having the error is 0, then your model is perfect. If your error is greater than 0, there is the possibility of error. So we try to we try to reduce the error close to the 0 by using the uh, uh, formula x transpose. X is the given input, so transpose into x inverse, and x transpose, this is the predicted actual value y. So by computing the inverse of the given matrix, this is the dot product matrix, so x transpose x inverse and x transpose dot y, we can update the parameter theta values. Here, what is the computational complexity for least square regression? When you are taking the n number of training samples with the c number of features, c number of features in the sense x values. X1 is one feature, x2 is second feature, x3 is third feature. So, but here we are concentrating on only one feature. So that is the thing here. So based upon the number of features, it will consume the complexity, time complexity, c square n. So the number of features into number of samples to multiply with x transpose by x. So here we are using the x transpose x. So based upon that, we will get the time complexity. And for multiplying the x transpose y, the we are getting the order of c and n. So we are in need of two steps of process. For two steps of process, one step is order of c square n and another step is order of cn, and third step is here order of n cube, because whenever the c is equal to n, suppose I am having the three samples and three number of features, so the another time we will get the c equal to n. So for computing that least square, here we are using the Cholesky factorization method of x transpose x to calculate the product of x transpose x inverse uh, dot product of x transpose dot y. The computational complexity for the normal equation will be order of n cube. Exactly, it will be order of n power 2.4 between the order of n cube. So approximately we can say order of n cube. For large set of features, 1 lakh of features, the normal equation computation will be very slow, because when you are changing the number of features c value, it is affecting the time complexity here based upon the number of features. And however, the linear equation handles the large training sets. Number of samples can be m, can be more, that means n. Here number of samples are represented by using the n can be large data set, but number of features should be low values, I mean less values, so the model can fit into the memory. Once the model is trained, then it will be fast. So for the training only it will take more time, but for testing the data points it will take less time. Here we will minimize the error by using the least square error function. Here the least square error function is calculated by using the distance between estimated uh, value and actual value. Actual value is y, predicted value is y dash. Then we will apply the least square method to find out the best fit line. This is the decision boundary which is best fit line in this given example. So here it can be minimized by taking the least square method, sum of the least square method. This is the total error. So for this from this total error we will try to minimize the error by updating the parameter value. Here I have given an example by using the least square error method. This is the least square error method. The given data points are 1, then actually output is 1, I mean x value is 2, for that actual output is 2, 2.5, actual output is also 2.5. Here we are taking the actually here the equation will be y equal to theta 0 plus theta 1 x1. So based upon that we need theta 0 and theta 1. Randomly we are taking initially theta 0 equal to 1 and theta 1 is 0.5. So based upon the hypothesis of x, this is the hypothesis of x, this is the hypothesis of x. Based upon that we will calculate the value. One is the theta 0 and theta 1 is 0.5 and x1 value. Based upon that, for first sample we are calculating. Here this is y dash, actually this is y dash, here also y dash, here also y dash, here also y dash. So y dash of first sample is when you are substituting the value here, this is the theta 0, theta 1, here x1. So when you are substituting the values you will get 1.5. For the second sample you are getting the 2.0. For the third sample you are getting the 2.25. So predicted values are mentioned here. For first sample 1.5, second sample 2.0, third sample 2.25. Then we are applying the cost function by using the linear least square error method. So this is the least square error method cost function. So we are applying y dash of first sample minus yi. So this is the y dash of first sample and y of first sample, and y dash of second sample, and y of second sample, and y dash of third sample, and y of third sample. So we are applying that, but then we are getting the 0.3125. So this is the error we getting. So this is the error for data point 1. There is no error. This is the error between the data points. This green color decision boundary is the predicted decision boundary based upon the predicted values, but this is giving 0.3, so which is almost close to the 0 value. So this is the better best fit line. Based upon the least square method we found the best fit line here for the given data set, this with 3 samples. Thanks for watching.